Consider a point mass m attached to one end of a massless rod of length r, where the other end of the rod is held in place. So hold this in place, and if this mass is rotating, then we can compute its kinetic energy. Of course, k is just 1/2 mv squared, but remember that v is r omega as something goes around like that. And so k is 1/2 mr squared omega squared, which I could write as 1/2 times the quantity mr squared times omega squared. Hopefully you can see that's just sort of an algebra game. There's nothing really deep going on. To be fair, that arrangement isn't particularly insightful, but gets more interesting if we have more masses, let's say 3 of them, where now we have m1 at a distance r1 from this point, m2 a distance r2 away, m3 a distance r3 away, and we let them spin like this. Now the kinetic energy is, of course, just the kinetic energy of each of them added up, so 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 m3 v3 squared. But each of the v's is an equivalent r omega, r1 omega and r2 omega and r3 omega. Notice, though, that they're all, while they each have their own r's, r1, r2, r3, they share omega. They're all rotating at the same angular rate. They complete an orbit in the same amount of time. So now I can do the same stupid algebra trick, and I can group the m's and r's together, and I have 1/2 m1 r1 square times omega square, and 1/2 m2 r2 square times omega square, and 1/2 m3 r3 square times omega square. But now I can pull it out and say this is 1/2 times some sum times omega squared, where the sum is m1 r1 square plus m2 r2 square plus m3 r3 square. And you can see that if I had more points, how easy I could generalize this to just say take each mass times its distance squared. Why is this useful? Because we already kind of know what kinetic energy should look like. Our kinetic energy starts off as 1/2 some inertia term times some speed squared. So we have a thing now that still looks like 1/2 times a speed squared, so we can identify this thing in here as some sort of inertia term. And then it still looks like our kinetic energy, 1/2 times inertia times speed squared. Just repeating that formula derivation here, we define this stuff to be called I. We symbolize it by a symbol capital I. And I is what's called the moment of inertia, which is an old-fashioned term wrapped up in 18th century mathematics. The more modern term is the rotational inertia. In other words, it's the equivalent of inertia for things that spin. It plays the role of mass for things that spin. Things that have high moments of inertia are hard to start spinning, and then they're hard to stop once they are spinning. It's like a mass, but it's not just the mass, and keep that in mind. Notice that it depends not just on how much we have, but how it's configured. Things that are further away from the rotational axis carry a greater weight in computing I. All of this is what makes rotation somewhat more complicated than the point particle motion that we've studied. In principle, if you wanted to find I, you would break any object down into pieces that were sufficiently small that you can consider them point-like. And each point-like mass, mi, has a moment of inertia equal 1/2 mi ri squared, where ri is its distance to the rotational axis. And then we just add them up. So I is the sum of all these things. But in practice, there's no way around it. This requires calculus, almost always, except for very symmetric things. And it's usually kind of messy. If the object has symmetry, we can simplify the calculation a lot. So often problems are done in terms of objects that have high symmetry, such as disks or cylinders or spheres. Not all symmetries are equally great, though. Like rotating a square is okay, but not fantastic. But rotating a disk is really easy. We'll do a little bit on finding the moment of inertia in a formal way, but it does require some calculus. You'll have to do some integrals. All textbooks like to give you the easy cases. The way the committee works is almost always in a problem they will either be asking you to find the moment of inertia, or they'll give it to you. And the ones that they generally expect that you're going to know, they expect you to know a thin hoop or cylindrical shell, a disk or solid cylinder, and then the long axis, a long rod. And then they generally don't expect you to know, but it's not bad to have some idea on the spheres. They do not generally at all require you to know these things. Sometimes they ask about them, but then they set you up to compute them. Do you need to memorize these? I would argue no. I would argue that like I said, they will basically come to them. Some of them are easy to get, though. For example, in a hoop, we have something, and we're going to rotate about that axis. All right, so here's our hoop, and we're going to spin it around that red dot. I'm going to pretend that it's a circle. My circle there was pretty bad, so let's instead draw a circle. Oops. Let's move the red dot. Oops. All right, well, let's mark the center. That was pretty bad. And then the idea is we're going to spin, say, this way. That really is not the center. But for a thin hoop, all of the mass is on the edge, so they're all at the same distance. So when I'm adding up mr square, all of the r's are the same, so it becomes the sum of the masses times r square. So it just becomes mr squared, as if they were a point particle. They're all acting as if they're at the same distance, and therefore as if they were all the same particle. But the others don't have easy explanations. The disk, for a solid disk, you find that it should be less at least. Why? Because on average, the mass is closer to the center than the edge. Most of the mass is located not at the edges. And so when we add mr squared, the r squares will be lower for those masses, so we'll get something less than mr square. But the fact that it comes out to be a half is this geometric oddity, which, again, we'll do when we do them explicitly. It is good to be able to look and say, I can tell the rough order of magnitude, even if I can't compute them very easily. One key takeaway, though, is that mass close to the axis counts less. Even if there's a lot of mass, if it's near the center of rotation, it doesn't play much role in inertia. For objects of equal mass, the more compact one will generally have a lower I, will always have a lower I. On the other hand, a small object far away from the rotation axis can carry each moment of inertia. For instance, Jupiter is only 1/1000th the mass of the Sun. But because its orbit is so large, if we consider the Sun and Jupiter being one system, Jupiter is almost 1/3 of the total rotational inertia of the solar system. So even though it's only 1/1000th the mass, the r² term wildly compensates. What's going on here, drawn, of course, not to scale, is here's the Sun, out here is Jupiter, and they're rotating. The Sun is doing some very small rotation around their center. That's exaggerated. But Jupiter is doing this huge rotation, and so its r is much bigger. All right, let's practice some. A rod is made of 3 segments of equal length with different masses. The total mass of the rod is 6m. And they show us here that the masses are 1/3 of the rod is length m of mass 2m, of mass m, the middle is of mass 2m, and the other end is of mass 3m. And they ask, will the moment of inertia be greater around the left end, the right end, or around the same ends? And we can sort of think of these as 3 point masses that are located at their symmetry points. So we can say, like, here and here and here. And so we can imagine we have either this arrangement or we have the opposite arrangement. And we're asking, we're going to rotate about the left end. So really, I shouldn't have drawn it quite that way. I should say they're either going to be rotating here around this point, doing this, or they're going to rotate around this point and keeping the sense the same, doing this. The key bit, of course, is that in the top case, most of the mass is really far away from the axis. Whereas here, it's a relatively small distance. And so the 3m is going to play a much greater role in this than in this. So we're going to end up that it must be greater about the left end. All right, here we have each of the 10 point masses in each case identical. The solid line in each figure represents an axis about which the mass is going to be rotated. The points are all fixed together so that they all maintain the arrangement shown as rotated. So imagine it's like a very thin net or something that they're on. And we're going to spin them, and they aren't entirely explicit, but well, I guess they are. They're going to spin them around this axis. So imagine them coming out of the page and then whirling around and going back into the page. And we want to draw a blue circle around the system or systems that have the hardest to start rotating, and a red circle around the systems that would be the easiest. But remember that this phrase means high rotational inertia. So we really want blue around the highest rotational inertias and red around the lowest. On the next screen, I'm going to compute them explicitly. Let's see if we can get some idea before we even go in. And what I will look at is that all the ones that have these three, these guys are not contributing at all to the value of I, because their distance is 0. Likewise, they don't contribute, and they don't contribute. So really, they're completely irrelevant. And then we can see that here we have a lot of mass near the axis and one pretty far away. Over here, we have still most of our mass near the axis, and the ones that aren't are relatively close, to a distance of 2 and 1, as opposed to a distance of 3 and 2. So you can sort of say this guy is the same as this guy, but we get more for this one being further out. The one that's going to be really impressive is this one, where there's some mass here, but a lot of the mass is very far out. So my instinct is that this is going to be the one that has the most. And then this one looks a lot like, say, this one. They're almost the same system, although not quite. So I don't know which of these will be least, but I think it will be one of those two. To actually know for sure, we should compute it. So what we would do is we take each of these and we'd say, like, this is m times 0 squared plus m times l squared plus m times 2l quantity squared, which is 4l squared. Actually, when I do it, I'm going to do vertically because they're all the same distance away from the axis. So I would do 3 times 0 squared plus 3 times 0 squared plus 3 times 0 squared. And 3 times 0 squared. And here we'd have 3 times 1l squared and 3 times 2l squared, 2l quantity squared, and then 1 times 3l quantity squared. And do the same for the rest. And this is how it all works out. And this is just some grungy algebra, so I'm not going to walk through arithmetic. But the basic idea for all of them is count up the number of masses and multiply by the square of the distance. In B especially, and a little bit in D, we have to be careful that this is on the left, but it's not at negative. Not that it would matter, but it's not negative. Its distance is 2L. And when we walk through it, it turns out that, in fact, as I said, we get 37 factor out here as low as a 13 factor, but B and D were somewhat close.